now it's time that we start the first presentation of one of the ESoC 2020 teams. And for this, I would like to invite Aditya Ahuja and Adithya Niranjan to talk about their project. They've been they applied AI on a very interesting task because they applied AI capabilities to address operation challenges in ECMWF products team. And the presentation is pre-recorded, but the Aditya, both Adityas are there for any questions you have. And so enjoy their project presentation.
Hi, I'm Aditya Niranjan.
And I'm Aditya Ahuja.
So today we'll be talking about our European Summer of Weather Code project, where we worked on building anomaly detection systems focused on detecting anomalies in ECMWF servers. We're really excited about this project because we feel this project can be extended to multiple ECMWF services, as well to general problems that require anomaly detection in a time series fashion. Moving ahead. So the particular use case we focused on, as mentioned, was on ECMWF's data services, where these provide huge amounts of information to end users. These get around millions of user requests every single day and deliver terabytes of data. So a particular downtime in any of these servers could potentially mean that hundreds of thousands of users' requests are delayed or potentially dropped. Ideally, catching a server downtime the second it happens or as soon as possible could save multiple of these, and this is what we try to do with machine learning. So the methods that we developed in this project are hand-tuned to work best with the data that we had, but this is very extensive. Moving ahead. This was the sort of data where we got raw log files from the server. Each log file corresponds to a completed request and gives us information about the start, stop, and how much data and what type of request was present. However, while this is a lot of information, we focused on a few particular fields that we felt had the most information about whether our server was not working well or was going to go down, and restructured it to work with our machine learning algorithms. We get around 1.5 million such logs a particular day. So this translates to a lot of data. Moving ahead. Once we processed the logs, we ended up getting information like this, where this particular example corresponds to the retrieve volume in bytes of mass OD on the 30th of April and the 1st of May. As you can see, there are two particular periods that are particularly interesting, where the service has gone down from somewhere around 8 p.m. to 9 p.m. And after the restart, which is marked in brown, the retrieve volume recovers partially before it again crashes. In both of these instances, there is a decent amount of gap between the drop and the corresponding restart. Ideally, we want to detect the drop at the edge so that it gives more people time to respond and also make decisions easier. Moving ahead. So while we focused on building this anomaly detection system, the first thing we considered was the open source anomaly detection algorithm implementations online. Most of them seem to have certain drawbacks, which led us to developing our own package. So firstly, a lot of them were focused on offline detection, which assumes that you have information happening after the time step you're predicting on, which means that you would not be able to predict real time with the same time scale that we have. Secondly, we have a lot of methods that we found having old and deprecated code bases where they were implemented in older versions of Python that no longer are supported, or there were some packages that were lacking. So this was a major issue in building a future friendly package. There was no common interface that we could combine multiple methods and compare and contrast or possibly ensemble these. So we wanted to build something that had joint information about all of these methods so that the end user can pick any of them depending on their freedom. Finally, there was no estimate for the robustness for the task at hand, in the sense that while each method used to give you a prediction, there was no confidence intervals or estimate of how well the system was working. The fact that we have multiple methods and a few uncertainty aware methods means that this extension is really useful. So as mentioned, we wanted to build an anomaly system that solves all of these problems. So what we built, we started off by taking up existing open source time series anomaly detection libraries, and then adapting them to work in streaming real-time data. We then implemented our own forecasting methods as an addition to these, where you could get anomaly scores by comparing what was forecasted and what the real-time result was. We did all of this in a multi-threaded fashion so that you could have algorithms training in the backend while you got real-time predictions. This means that the algorithms could be continuously retrained on new data as it arrives and makes the system more robust overall to changes in the data or trends. Finally, we have a interface where the end user can view the time series and the anomaly score on their browser or very easily. Oh, yeah. So just to put everything together, this is the sort of pipeline where we built, where you have, starting from the log files, a system that takes them, parses them, and clubs them together into a time series. Then you process this time series to work well with individual methods. So that's a custom pre-processing, followed by training for each of these models. And once you have trained these models, we get these predictions, each of these having a different threshold above which we consider this to be anomalous. The end result is something that it can generate alarms potentially as a message to the end server administrator or an email or any sort of notification. The two flows that we have here are the solid line representing the offline process, which takes time and happens every few days where the models are retrained, and the dashed line representing an online pipeline, which uses information from the offline process to predict every few minutes or every few time scales that is a user parameter. So going ahead to the results, my teammate Aditya Ahuja will take over and will present some of the results of our method. Thank you.
Hello everyone. So I am Aditya again, and we have some results. And after all the theoretical background and explanations, now we want to see how really do our methods work on the problem that they were initially designed to solve. So as a motivational use case, we have this example from 10 June, and we have a downtime over here between 2 a.m. and 6 a.m. and we can see it's a 4-hour period, and this downtime was detected at 6 a.m. when it was finally fixed, and so there was a gap of say 4 hours in between. Moving on to how our method performs on this. This is our real-time method. At the top over here, we have the time series in green, which is the input to our method. And at the bottom over here, we have the anomaly score, which is the output from our method. And over here, our method detects this anomaly right when it's about to start, or when it's just started. So it detects it at around 2 a.m. And so we get a 4-hour window, which and we can potentially save the requests in that time period. So going back to Niranjan's initial 1.5 million requests per day estimate, that saves about 250,000 requests for this particular downtime alone. And so this was an easier downtime to actually detect, but our method also performs well on more difficult downtimes. So this is another difficult downtime which was given basically as a label. And so this was an actual downtime which we had to detect. And our method also performs well on these tasks. So this is the same downtime. And again, our method does give a very good score on downtimes like these as well. So we just went through two potential examples of how our method works on the real data that it was built for. And we can go into more detail on how our method works in the upcoming demo, which we'll see in 2 or 3 slides. So going into the challenges and learnings from this project, I believe that the major challenge we faced was that the labels that we had were not really representative of the downtimes in a complete sense. So we did have periods where the machines were down, but we didn't have any idea of when the downtimes actually started. So we had to do a lot of analysis and a lot of basically graphing to actually understand what happens during a downtime and how we can extend those labels to actual intervals which our algorithm should detect and on which they can be trained on. So we also had another problem that we had to keep a lot of real world constraints in mind. So even though we were given data for over 2 months, we had to make sure that while predicting for up to a specific point, we only use data until that point and nothing after that. So we had to make sure that we don't leak data from the future into the predictions for the current moment. So these were some of the challenges, and we also learned a lot. We learned a lot about time series and anomaly detection and forecasting, and we read a lot of papers and we understood their applications. I believe more importantly, we understood how current methods are limited in certain ways and in what direction we should go if we want to extend them. And we basically learned that it's very important to have methods which work in real time, because most of the current industrial applications require these methods to work in real time. So you can't have an anomaly detection system that detects anomalies on metrics from a week ago. You want it to work in real time. And this is why we believe our method is very important. We also learned a lot about software development, and we basically had to build an end-to-end system, and we believe that was a very good learning experience. So moving forward, I can give a short note on how you can extend our method for your own task. So at the core of our methods are the anomaly detection modules, which are basically trained on the time series that have been generated from the logs that are being passed from the parser module. So to extend these to your own data, what you need to do is you need to modify the parser function and then get the new time series, and then you can just tune the hyperparameters and actually get these methods to work on your own time series. And we have a readily available package on GitHub, and we believe it is very easy to extend this to other methods, and we'll be open for chats on how if you have any specific queries in mind. So all this aside, we'd like to show a real-time demo of how our project works. So I'm over here. I'm logged into ECMWF servers, and I have installed the Black Swan package. So I can just run the package, and it initializes all the different methods, and then it starts training on one specific method. And after training, we have the predictions. So it continuously evaluates as well as trains for other incoming data. So over here you can see it's continuously training. And we can also start the real-time plotting module. So this is the plotting module, and it basically serves the plot at this URL over here, which I can then reroute to my own machine and have it served in real time in my browser. So this is Chrome over here, and I have the system basically outputting the plot to my own machine. At the top, again, we have the time series, and at the bottom, we have our methods output. And we have a variable y-axis, which can help us understand how a specific anomaly score is in relation to the ones near it. So it adjusts based on how big current anomalies are. So this is how our system works. We also have some additional functionality, such as you can zoom into specific points and basically examine them. And you can also take screenshots and do other things. So this was our method that we developed. And so moving on, we also have some sample figures as well as videos of how other methods work. So this was our project, and we believe that this wouldn't have been possible without our mentors and the wider ECMWF community. So specifically, we'd want to thank Marcus, Peter, Manuel and Victorus, for their amazing mentorship and guidance, as well as everyone from ECMWF and everyone in the ESoC project, and who helped make all this possible.
Yeah, we've had really great support, particularly in the backend. We've had a lot of support from the Morpheus Cloud team, and Esperanza, Julia have always kept us up and given us a huge amount of encouragement. There are a lot of people we really like to thank. Sorry if we missed out a few, but this has been an amazing experience. Thank you.
So now we'd be happy to take your questions. Yeah, thank you.
Okay, thank you, Aditya, and also thank you, Aditya. It's amazing to see your project, and I have actually one question before we go to the next project. So, do you know? So, what is now the current state? Can this, what you have now, can this be already implemented in ECMWF on the products team? So they already use it, or are there plans to use it?
There are plans to use it. We're working with Peter and our mentors in just getting it to it. So we'll be continuing for a bit more time to ensure this goes to production.
Yeah, so currently we have the whole system working with the specific logs from Mars itself. And so there's no extension needed, but we do need to tie up a few loose ends at some places. But by and large, the system is ready, and the main chunk of the machine learning part is done.
Oh, wow. Okay, this is very impressive, like very well done.